Between 1939 and 1945, Germany manufactured more than 100,000 planes, 46,000 tanks, and millions of rifles and machine guns. It was the most vast industrial apparatus ever created for a war. However, when the Reich collapsed, a significant part of that arsenal vanished without leaving a documentary trace. Abandoned factories and incomplete plans gave account of a colossal effort interrupted abruptly by the collapse. In the Harz Massif, the tunnels of Mittelwerk remained active even days after the surrender, with V-2 rockets ready to be moved. Thousands of tons of bombs and chemical weapons were sunk in the Baltic Sea. The Allies recorded as much as was possible for them, but numerous projects never appeared in the official reports. At the same time, hundreds of scientists were captured by the winning powers to take advantage of their knowledge and accelerate their own military and technological programs, among them Werner von Braun. The knowledge was exploited, but the destiny of a great part of the armament remained without being clarified. What happened with the weapons of the Third Reich that no one saw again? 1945, when the arsenal of the Reich collapsed. At the beginning of 1945, the German military apparatus no longer functioned as a coordinated system. The structures that had sustained the production of armament for years remained standing on paper, but in practice they were paralyzed. The factories continued existing, the organizational charts had not been dissolved, and the orders continued being issued from Berlin, although the real capacity to transform those orders into usable weapons had evaporated. The problem was not a single lack, but the simultaneous accumulation of failures that affected each stage of the productive process. The war industry depended on a complex network of supplies that included steel, coal, electricity, railway transport, and specialized labor. At the end of 1944, none of those elements was guaranteed. The coal mines operated intermittently, the blast furnaces functioned below their capacity, and the power plants suffered constant cuts. The production of steel, which had been the pillar of the armament effort, fell abruptly. Without steel, cannons, armor plating, nor structures for vehicles could not be manufactured. The stocks accumulated during the previous years were consumed rapidly and could not be replenished. The railway system, essential for moving materials and finished products, was in a critical state. The Allied bombings had destroyed key nodes, repair workshops, and locomotive depots. The trains that managed to circulate did so with prolonged delays and incomplete routes. Wagons loaded with parts remained immobilized for days or weeks in secondary stations without the possibility of continuing. In many cases, the materials never arrived at the plants where they were to be assembled. The Allied aviation had achieved something that for years had seemed impossible: to interrupt in a systematic way the German industrial production. It was not only about destroying buildings, but about breaking the rhythm of work. The factories were evacuated, repaired in a provisional way, and attacked again. The workers spent more time moving, hiding, or rebuilding facilities than producing armament. The result was a sustained fall in the quantity and quality of the material delivered to the armed forces. The lack of labor aggravated the situation even more. Millions of workers had been recruited for the front or displaced by the combats. The prisoners and forced workers who occupied their place lacked, in many cases, the necessary training for complex tasks. The constant rotation and the physical deterioration reduced the efficiency. Even when the machines continued functioning, the number of defective pieces increased and the deadlines were missed in a habitual way. In the last months of the war, the authorities tried to maintain the appearance of control. Plans were issued, ministries were reorganized, and production objectives were announced that no longer had relation with reality. The official figures continued being recorded, but they did not reflect what occurred on the ground. The distance between the reports and the real situation became increasingly greater. The production of tanks, planes, and heavy artillery descended to levels that did not allow sustaining military operations of magnitude. At the same time, decisions were taken to destroy part of the arsenal itself. Before the enemy advance, it was ordered to disable facilities, blow up depots, and sabotage equipment that could not be evacuated. These actions did not respond to a strategy of conservation, but to the attempt to prevent the material from falling intact into opposing hands. In numerous cases, the orders were executed in a partial or chaotic way, but even so they contributed to reducing the quantity of armament available even before the formal surrender. The production of ammunition, which had been one of the most resistant sectors, was also affected. Without reliable transport and with damaged factories, the projectiles did not arrive at the units that needed them. The warehouses were emptied in some fronts, while others accumulated unusable stocks for lack of compatible weapons. This discoordination reflected the breakdown of the logistical system that had sustained the army during the initial phase of the war. The collapse was not uniform. Some plants continued producing until the last moment, while others ceased their activity months before. However, even in the centers that remained operative, the production lacked continuity. The interruptions were constant, and the final products rarely met the planned standards. The idea of a coherent arsenal ceased to make sense. What existed was a sum of isolated efforts without capacity to converge in a common objective. In this context, the concept itself of Arsenal of the Reich lost its practical meaning. It was no longer about an organized reserve of weapons ready to be deployed, but about scattered fragments of a system that had ceased to function as a whole. The war had surpassed the material capacity of the German state to sustain it. The wear accumulated during years manifested in an irreversible way in 1945. When the Allied forces advanced over the German territory, they found an industrial landscape marked by destruction and paralysis. Many factories were empty, others damaged to the point of not being able to resume their activity without a complete reconstruction. The armament programs that had been priority were cancelled de facto, not by strategic decision, but by material impossibility. The lack of resources had imposed its own limit. The end of the armament effort did not arrive with a formal announcement, but as a result of a chain of failures that reinforced each other. Each lack made it more difficult to solve the following ones. Without energy there was no production, without transport there was no distribution, without qualified labor there was no reliable assembly. The system collapsed from within before being dismantled from without. In May of 1945, what remained of the German arsenal did not represent a usable force. It was the residue of an exhausted industrial apparatus, incapable of sustaining a modern war. The deliberate destruction, the constant interruptions and the loss of control had reduced that arsenal to a series of unconnected remains. The Reich had not only lost the war in the field of battle, but also in the material terrain that had made its initial expansion possible. The collapse was total because it affected the very base of the military power. Without continuous production, without functional logistics, and without capacity for replacement, the existing weapons ceased to be a strategic resource. They became isolated objects, without a system that integrated them. At that point, the arsenal ceased to exist as such. Only the tracks of an industrial effort that had reached its absolute limit remained. The total disarmament of Germany, factories, weapons, and scientists under control. After the German surrender, the territory remained under a control system designed to prevent any military reactivation. It was not only about occupying cities or dissolving armed units, but about neutralizing in a permanent way the material base that had sustained the war. The country concentrated thousands of industrial facilities linked directly or indirectly to the armament, besides large volumes of specialized machinery, strategic materials, and finished products. The priority was to cut that capacity from the root. The initial orders established the total prohibition of manufacturing weapons, ammunition, and military components. This prohibition extended to any activity that could sustain the war production, including precision tools, smelting equipment, optical systems, motors, and specific metallurgical processes. The measure affected complete sectors of the industry, many of which had oriented their activity almost exclusively to war contracts for years. The cessation was immediate and did not admit exceptions. The physical dismantling became the axis of the control. The occupation authorities identified key plants and proceeded to disable their productive capacity. Machine tools of great size were disassembled and withdrawn. Presses, lathes, industrial furnaces, and assembly lines remained out of service. In numerous cases, the equipment was destroyed on the spot. In others, it was loaded and moved out of the country. The objective was not to conserve, but to eliminate the technical possibility of producing armament, even if the will to do so existed. The scale of these operations was wide. In entire regions, the withdrawal of machinery affected the industrial structure for years. It was not about isolated pieces, but about complete sets of equipment that had required prolonged investments and accumulated specialization. The loss of these assets reduced in a drastic way the capacity for heavy and precision manufacturing, even for non-military uses, and altered in a profound way the local productive fabric. The seizure of the existing material followed systematic procedures. Depots, arsenals, and workshops were inspected one by one. The finished weapons were recorded and withdrawn from German control. This included large quantities of rifles, machine guns, artillery pieces, and stored ammunition. In many cases, the material was scattered, incomplete or poorly conserved, but even so it was considered part of the war effort and submitted to control. The logistics of the seizure demanded an extensive administration. The volume of material was such that its withdrawal could not be completed in few days. Inventories were organized, warehouses were sealed, and custodies were established to prevent unauthorized accesses. There, where the immediate transport was not possible, it was opted to immobilize the material until its withdrawal or posterior destruction. The priority was that nothing remained available for an autonomous use. The control extended also to the auxiliary facilities. Secondary workshops, subcontracting networks, and maintenance centers were included in the inspections. The war production had not depended only on large visible factories, but on an extensive network of small establishments that provided pieces, repairs, and services. Identifying them and neutralizing them was an essential part of the process, supported by industrial documentation recovered during the war. The measures were not limited to the objects, they also affected the people linked to the military production. Technicians, engineers, and managers were identified and submitted to restrictions. Many remained separated from functions related with armament and sensitive machinery. The technical knowledge was treated as a strategic resource that should be controlled in the same way as the factories and the equipment. The intention was to prevent the internal reorganization of capacities, even in the absence of material. In the institutional plane, the structures that had coordinated the war production were dissolved. Administrative organisms, departments, and chains of command that connected political decisions with industrial planning ceased to operate. Without those structures, any attempt to reactivate the production lacked legal and organizational framework. The disarmament was, therefore, physical and institutional at the same time. The differences between occupation zones influenced the application of these policies. In some areas, the control was combined with conversion plans towards civil uses under strict supervision. In others, the dismantling was more direct and exhaustive. In both cases, the result was the definitive loss of German control over the means of military production. The capacity to decide what to manufacture, how and with what resources ceased to exist. The control extended to the scope of research and technical training. Centers of study, laboratories and universities remained subject to rules that prohibited works related with armament or technology of military use. Even investigations of theoretical character were restricted if they were considered applicable to war ends. This policy sought to close any indirect way toward rearmament, not only the most evident ones. The economic impact was immediate and profound. Entire companies disappeared as a result of the prohibition and the dismantling. Sectors that had absorbed large volumes of labor remained without activity. The adjustment was abrupt and affected hundreds of thousands of workers. From the perspective of control, these consequences were considered acceptable against the objective of eliminating in a durable way the material base of the war. The administration of the confiscated material was prolonged during months due to its volume. Even so, the direction of the process was constant. Each machine withdrawn, each weapon seized, and each facility disabled reduced in an irreversible way the possibility of reactivating its own military apparatus. The control was not conceived as a temporary measure, but as a structural condition. With the pass of time, these actions were integrated into a stable system of supervision. The disarmament ceased to be an immediate response to the end of the conflict to become a sustained policy. The combination of legal prohibitions, physical dismantling, and administrative seizure closed any space for an autonomous recovery of the war capacity. The territory remained submitted to a regime in which surveillance and regulation formed part of the normality. From this point, the weapons, the factories, and the resources no longer responded to internal decisions. Everything related with the old military effort had been separated from German control and put under external administration or eliminated. The process transformed in a definitive way the relation between the country and its capacity to produce armament not as a pause but as an effective rupture. the most valuable booty of the war, the German brains. The end of the war left thousands of German scientists, engineers and technicians without direction, many of them responsible for the most advanced projects of the regime. In the middle of the general collapse, the winning powers understood that future supremacy did not depend anymore on territories nor on massive armies, but on the technical and scientific knowledge that had allowed Germany to develop unprecedented weapons. What began as a process of interrogations and confiscations turned soon into a frenetic competition to appropriate minds, documents and technologies. From the first days of the occupation, American, British and Soviet military teams advanced with precise lists of people and laboratories to locate. Each side tried to arrive first. In abandoned or semi-ruined facilities, piles of plans, rocket pieces, encrypted files and boxes with incomplete experiments appeared. Many scientists surrendered voluntarily, conscious that working for the winners could be the only way to survive and avoid a trial. Others were located by patrols or denounced by neighbors, and their destiny depended on the officer who found them. The secret program that the Americans organized began in an informal way in 1945. Its purpose was to move the most valuable specialists to North American territory, even if their political past turned them into candidates for exclusion. The priority was their knowledge. In a short time, lists were elaborated with hundreds of names of physicists, doctors, engineers and technicians, many of them with direct links with the old regime. The plan grew until including more than 1,600 people and their families, a contingent sufficient to found entire research centers. The initial bases of this operation were established in Europe under a strict secret. The scientists were concentrated in military facilities where they were offered lodging, food and the possibility of continuing their works under supervision. In exchange, they should cooperate and provide all the available information about their projects. The interrogations were centered on missiles, jet planes, chemical and biological weapons, and new techniques of medicine applied to combat. Each data was valuable in a context in which no power wanted to remain lagging. The officers in charge of the program knew that time played against them. The Soviets advanced with rapidity and offered similar conditions. In many regions, the same scientists were disputed by both sides. Some changed sides according to the circumstances, others tried to negotiate their destiny. The result was a true race to secure the greatest possible quantity of German knowledge before the territory remained divided definitively. In practice, the process implied breaking its own rules. The rules that prohibited employing members of the Nazi Party or of paramilitary organizations were softened or ignored. The decisive thing was their technical utility. Engineers linked to the development of rockets, chemists who had worked on toxic armament, and doctors who had participated in experiments were recruited without publicity. The security reports that warned about their antecedents were modified or remained archived to not hinder the moves. The transport of these specialists was realized under military cover. Entire groups were moved by air or by sea, accompanied by documents, samples and prototypes. Each move represented a small blow of intelligence. The records detail the movement of tens of wagons loaded with pieces of rockets, equipment of laboratories and boxes of technical reports. Many of these materials were unique and constituted the base of the knowledge that later would define modern military technology. The engineers who had worked in the missile programs were of the first ones to be sent. Their knowledge about propulsion, guidance systems and fuels were considered strategic. Also, teams of doctors and physiologists were moved who had developed techniques of human resistance in height and acceleration, applicable to aviation and to the future spaceflight. In parallel, chemists and physicists with experience in explosives and combat gases began to collaborate in American laboratories under military supervision. The rhythm was that of a covered operation. Many of the recruited scientists did not possess valid civil documentation, nor had passed through processes of political review. They were granted special permits, temporary residences, and military salaries. Their families were taken to safe zones, and they were provided controlled lodging until the situation stabilized. The entire program functioned with a level of discretion that avoided public scrutiny. Meanwhile, the authorities justified internally these measures as a question of national security. The military reports affirmed that the recovered technical information was equivalent to decades of research and that allowing its loss would benefit the adversaries. The justifications appealed to the imminent rivalry with the Soviet Union, which already was outlined as the new threat. In that climate, the ethical limits were displaced in favor of the urgency. The Soviets applied a similar method, although with less concealment. Entire teams of specialists were moved toward the east, many of them with their complete laboratories. In a matter of months, hundreds of German scientists worked for Soviet programs of rockets, aviation, and advanced chemistry. The competition between the blocs became evident before the Cold War existed formally. In the western side, the recently formed research centers began to produce results. The tests with rockets in the American desert demonstrated the value of the acquired knowledge. From those experiments arose the first programs of guided missiles and the foundations of the future space exploration. In military laboratories, new substances were developed and methods of chemical and biological defense were perfected. What had been born as an operation of confiscation was transformed into a direct transfer of scientific power. The secrecy was absolute. The identities of many participants were kept hidden during years. Some of those involved in more compromised projects worked under false names or were moved with modified files. The official record spoke of technical experts without detailing their origin. The politics was subordinated to the convenience. The essential thing was that the knowledge passed from one side to the other without delay. In a matter of months, the winning countries had divided among themselves the scientific heritage of the Reich. The German knowledge was scattered in multiple directions, feeding the programs that would define the following decades. What for some had been the base of the war, for others became the starting point of a new technological era. The race to keep the best of the enemy had begun, and its result would mark the difference between military power and dependence. The weapon that changed the century, the German rockets. In the coast of the Baltic, between dunes, marshes and forests, one of the most secret facilities of the Second World War was raised. There, in Peenemünde, hundreds of engineers, technicians and soldiers worked on a project that would change the history of the war and of the science. In 1936, the place was barely an isolated terrain. In few years, it was transformed into a complex with more than 500 buildings, landing strips, test tunnels and combustion banks capable of resisting temperatures superior to 2,000 degrees. Its objective was to convert into reality an idea that seemed impossible. A rocket of long reach capable of traveling faster than the sound and reaching another country. The development began with a reduced group of young engineers passionate about astronautics. They dreamed about space, but the army saw in them a military opportunity. Under military direction, the team started to design liquid fuel engines of increasing thrust. The first models barely rose some meters before exploding, but each attempt served to adjust valves, pressures and mix proportions. With time, they managed to stabilize engines that surpassed 25 tons of thrust, the sufficient to launch a load of 1 ton to hundreds of kilometers of distance. The technical progress was rapid because the regime destined resources without limits. Peenemünde had its own electrical network, metallurgical workshops, materials laboratories and meteorological stations. Each department was specialized in a different aspect: flight control, combustion, structures, aerodynamics, gyroscopes. More than 3,000 people worked there daily. The most experienced engineers supervised teams of apprentices, while the officers of the army controlled each decision. The hierarchy was rigid, but the technical freedom was wide. The important thing was to obtain results. The trials multiplied week by week. In the test fields, rockets of different sizes were launched, each one numbered and documented. Trajectories, temperatures and failures were recorded. Some engines were turned on during few seconds before catching fire. Others managed flights of several kilometers. The calculations were realized by hand or with slide rules, and the data was stored in thousands of sheets that occupied entire rooms. The atmosphere combined scientific enthusiasm and military pressure. No one could speak about the project outside the enclosure. In parallel, facilities were built to measure the resistance of the metal to extreme heat and to test new alloys. The depots stored thousands of liters of alcohol and liquid oxygen, the two basic components of the fuel. Each launch required tanker trucks, cranes, and a team of more than 100 people. The errors could be fatal. A leak of oxygen or a poorly sealed valve were enough to provoke an explosion. In spite of that, the accidents were considered an inevitable part of the process. The cost of the project grew in a vertiginous way. The budgets were counted in hundreds of millions of marks and surpassed those of many aviation programs. The priorities of the regime maintained it at the top, even when other sectors suffered cuts. As the tests improved, the political leadership began to see the rocket not only as an experiment, but as a weapon capable of altering the course of the war. That expectation pushed an acceleration that forced producing results before having completed all the phases of development. The tests of 1942 marked the first great success. A rocket managed to reach almost 90 kilometers of height and travel more than 200 kilometers of distance before impacting in the sea. For the first time, a human artifact had brushed the edge of the space. The military observers understood that they found themselves before a completely new weapon, impossible to intercept and of an unprecedented reach. The enthusiasm was immediate. The production in series was approved under the name of A4. The jump from the prototypes to the manufacturing in mass posed enormous challenges. Each rocket contained more than 30,000 pieces and required minimum manufacturing tolerances. The precision of the gyroscopes, the sealing of the tanks, and the quality of the fuel were critical. To sustain the rhythm, departments of quality control were created, and the assembly plants were expanded. However, the pressure for delivering results led to rushing processes. Many rockets ended unusable before arriving at the field of launch. Peenemünde turned into a militarized city with thousands of employees, an airstrip, housings, and internal services. The daily life combined industrial routine with absolute secrecy. The workers worked shifts of 12 hours, and the engineers slept next to the laboratories to supervise nocturnal trials. In the nearby docks, ships docked with components proceeding from all occupied Europe. The supplies arrived escorted by patrols and were unloaded directly in the workshops. The program attracted foreign observers. The Allied espionage missions tried to photograph the facilities from the air. The reports about a supposed giant rocket project began to circulate among the intelligence services, although during a time they were considered exaggerations. Only when a British plane captured images of large launch ramps, the Allied command understood the magnitude of what was being built. In 1943, the production began officially. The first lots of rockets were assembled and were prepared for combat tests. The loads of explosives were installed in the frontal sections and the guidance systems were adjusted. The technicians calculated that the projectile would reach the target in less than 5 minutes after the launch, a speed superior to any bomber. The sensation of power was enormous, but also the pressure grew. Each failure supposed the risk of losing years of work and resources. The Allied bombings over the north of Germany changed the destiny of the project. In August of 1943, a series of attacks destroyed part of Peenemünde, killed hundreds of workers and left the launch strips unusable. The surprise was total. For the first time, the Allies had hit directly the heart of the program. Those responsible understood that they could no longer maintain the production in sight. It was decided to move the assembly to an underground zone, more safe and secret. That move marked the end of the laboratory stage. Peenemünde ceased to be a center of innovation and became a memory of the initial enthusiasm. What followed was a forced production in extreme conditions, very far from the Baltic coast. The same engineers who had dreamed about conquering the space should direct a factory hidden in the interior of a mountain. The science mixed definitively with the war and with the human exploitation. The dream of Peenemünde had demonstrated that it was possible to manufacture a rocket capable of crossing continents, but also it had revealed the cost of doing it under a regime desperate for achieving an impossible victory. In the ruins of the laboratory remained the remains of an ambition that had surpassed all known limits. What there began soon would go out from the tunnels of the hearts toward the sky in search of its last destiny. After the bombings over Peenemünde, the German command decided to move the production of rockets to a place that could not be reached by the Allied planes. The Harz Massif was chosen in the center of the country, where mines and tunnels capable of hiding an entire complex underground existed. There, in humid galleries and without ventilation, a factory of more than 20 kilometers of tunnels known as Mittelwerk was raised. The construction and the functioning of the site remained under control of the SS, who administered it with a combination of military discipline and absolute brutality. The move was realized in all haste. Hundreds of wagons loaded with machinery, molds, tanks and pieces left Peenemünde toward the south. The improvised railway tracks arrived until the mouths of the mines. The workers unloaded the material by turns and mounted new lines of assembly under a mountain of stone. Definitive plans did not exist. The sections were improvised as the excavations advanced. The objective was to produce thousands of rockets a year without the Allies being able to detect it from the air. The labor came in its greater part from prisoners. Each day, new transports arrived proceeding from concentration camps. The detainees slept in improvised barracks inside the complex, without light nor heating. Many worked shifts of 12 to 16 hours in conditions of hunger and disease. The air was loaded with metallic dust, combustion gases, and constant humidity. The posterior reports estimated that more than 20,000 people died during the construction and the functioning of Mittelwerk, a figure superior to the number of civilians dead by the rockets launched against England. In the workshops, the engineers tried to maintain a balance between the production in series and the technical control. The extreme complexity of the system made that any error in a valve or a seal could provoke the explosion of the engine. The military supervisors pressured for quantity, not for precision. The prisoners, exhausted, committed inevitable errors. The defects were hidden to avoid punishments. Even so, each month between 500 and 600 rockets went out from the complex, ready to be moved to the launch depots. The process began with the manufacturing of the central body, a metallic structure of 14 meters of length and almost 2 tons of weight empty. In another section, the alcohol and liquid oxygen tanks were mounted, separated by insulating panels. The engines, with combustion chambers of tempered steel, were tested briefly in underground test banks. The explosions were frequent. A single leak could destroy a complete tunnel. The vibrations shook the mountain and provoked partial collapses. Despite the accidents, the rhythm did not diminish. The finished rockets were moved in closed trains toward exterior assembly centers. In each shipment, armed technicians traveled to guarantee the secret. The journey could last several days, crossing regions in ruins. Sometimes the trains were detained by bombings or lack of fuel and remained immobilized with their explosive load. The loss of a single convoy was equivalent to weeks of work. However, the pressure to supply the launch units grew with the desperation of the High Command. In Mittelwerk, also modified versions of the V-2 were developed. Some engineers worked on more precise control systems, others on rockets of greater reach. It was experimented with chemical loads and with adaptations for submarines. None of those projects reached the operative phase, but they left record of the technological ambition that still existed even in the last months of the Reich. The lack of resources and the logistical collapse prevented its culmination. The organization of the complex followed a strict military order. In the superior part, the engineers and officers were found, housed in barracks with heating and rationed food. In the inferior levels, thousands of prisoners slept in bunks of humid wood. The punishments were daily. Any failure could cost the life. The bodies were piled in lateral tunnels before being moved to the exterior. The smell of fuel mixed with that of the generators and the decomposition. In the middle of that environment, the most advanced technology of the world was manufactured. The scale of the project was reflected in the numbers. In its maximum point, more than 6,000 people worked in the complex, some 3,500 permanent prisoners and 2,500 technicians and guards. The monthly production was around 900 tons of material. Each rocket required around 16 tons of fuel, of which 2/3 were ethyl alcohol. To supply it, entire refineries were destined to the distillation process. The logistics of the fuel became so complex that additional underground tanks were installed. The efficiency reports elaborated in the last months of the war show that more than half of the rockets went out with manufacturing failures. Some lost control during the flight, others exploded when turning on the engine. In spite of that, the program was maintained in functioning until April of 1945. The production orders continued being issued even when the fronts were at less than 100 kilometers. No one dared to stop it without direct authorization. The secrecy was absolute. Only a few officers of the army and the SS knew the real volume of the production. The prisoners did not know what they were building. They barely saw metallic pieces and tanks. The engineers spoke in codes and the orders were transmitted in a fragmented way. It was prohibited to mention the word rocket even inside the enclosure. The letters and the reports were signed with acronyms and numbers. This level of confidentiality was an obsession. The project should remain invisible until the last day. When the Western Front approached, the directors of the complex received instructions to destroy everything that could not be evacuated. The controlled explosions began to be heard inside the mountain. However, the magnitude of the place made it impossible to erase the evidence. When the Allied troops arrived, they found hundreds of complete rockets, stored engines and tunnels still operative. The initial reports calculated that at least 150 projectiles ready for launch, and others as many in assembly remained. The liberation of the complex revealed the brutal contrast between the technology and the human condition. The precision machines were aligned next to bunks infested with lice and piles of bodies. The North American technicians remained impressed by the level of industrial development, but also horrified by the human cost. In the records they found production diagrams, daily statistics, and lists of dead workers. Everything remained documented with the same meticulousness as the flight trials. The legacy of Mittelwerk was double. It demonstrated that Germany had managed to build a technologically revolutionary weapon, but at the price of turning its development into a system of industrial extermination. The tunnels of the Harz were transformed into a symbol of that paradox, the place where science and barbarism coexisted under the same mountain. At the beginning of September of 1944, the first operative rocket was launched from the Dutch coast toward London. The projectile ascended almost 80 kilometers and descended at more than 1,500 meters per second. No defense could intercept it. The impact opened a crater of several meters and destroyed entire blocks. The era of supersonic weapons had been born. The German observers recorded each detail of the flight and sent the results to the High Command as proof that they still could hit the heart of the enemy. The launch system required a complex logistics. Each firing unit had tanker trucks, generators, and mobile cranes at its disposal. Preparing a shot could take more than 6 hours. The fuel should be maintained at extreme temperatures, and any leak provoked instant fires. The teams moved constantly to avoid the Allied bombings. In muddy fields, under the rain or the snow, the technicians placed the rockets over improvised platforms and calculated trajectories with optical instruments. Despite the theoretical precision, the margin of error was wide. Many missiles deviated tens of kilometers. During the following months, more than 3,000 V-2 rockets were launched. Close to the half failed in the flight or did not reach their objective. Those that impacted caused more than 9,000 dead and tens of thousands of injured. The figures were smaller compared with the Allied bombings over Germany, but the psychological effect was devastating. The affected cities lived with the sound of explosions that arrived without notice. There were no sirens nor shelters capable of protecting the population. The British reports described the impact as silence and fire simultaneous. The sound arrived after the destruction. The German command interpreted the results as a signal of hope. Although the weapon could not change the course of the war, it demonstrated that Germany still possessed a technological power unreachable for its enemies. The propaganda presented the V-2 as the weapon of vengeance that would balance the losses. In practice, the program consumed resources that the country already could not replenish. Each rocket cost as much as a modern fighter, and its manufacturing implied the sacrifice of thousands of enslaved workers. As the front collapsed, the continuity of the project became unsustainable. The last waves were launched from Holland and the northwest of Germany at the beginning of 1945. The objectives included London, Antwerp, and Liège. Many missiles fell in the sea or exploded in the air. The launchers were destroyed by the bombings before being able to relocate. The transport convoys were attacked by Allied fighters, and the railway routes remained cut. In March, the engineers received the order to evacuate the remains of the program. The tunnels of the Harz were filled with explosives to avoid their capture, although the magnitude of the complex made it impossible to destroy it completely. When the American forces arrived at Nordhausen, they confirmed the magnitude of the underground complex and of the technological material that had not been able to be destroyed. On the walls, still technical schemes and calibration tables hung. The intelligence reports qualified the find as the most important technological booty of the war. In the following days, specialized teams began to dismantle the projectiles and to pack the components for their move. In less than a month, hundreds of tons of material were sent by train and ship to North American laboratories. The Soviets, who occupied the eastern sector, realized similar operations. They captured factories, documents, and technical equipment. In some cases, the units of both sides were found at few kilometers of distance, looking for the same objects. The division of the territory determined the future of the technology. What fell in American hands fed the missile programs of the Pentagon. What remained in the Soviet zone turned into the base of its space industry. The rivalry that would define the Cold War was born literally among the remains of the V-2. In the test fields of White Sands in New Mexico, the North American engineers rebuilt the rockets with original pieces and German supervision. Between 1946 and 1951, more than 60 experimental launches were realized. Each one provided data about control, combustion, and atmospheric stability. The results allowed developing the first American guided missile and set the basis of the future space rockets. The technical manuals conserved the original names and measures. Valves, pumps, turbines, and navigation systems continued being the same, although under a different flag. In the Soviet Union, the experiments were realized in bases close to Moscow and later in Kazakhstan. The German technicians were moved with their families and worked under surveillance. In few years, the tests with models derived from the V-2 culminated in the first Soviet long-range missiles. The scientific and military competition was born from a same origin, the tunnels where the weapon of the Reich had been manufactured. The Allies took advantage also of the knowledge of the laboratories of materials, aerodynamics and propulsion. Institutes dedicated exclusively to studying the techniques of welding, the alloys resistant to heat and the inertial guidance systems were created. Each component of the V-2 turned into an object of study. The main engine, with its combustion chamber of steel and its 18 injectors, inspired posterior designs. The fuel pumps, capable of moving hundreds of liters per minute, were replicated in North American laboratories. The secret reports recognized that the defeated Germany had developed a technology between 5 and 10 years advanced regarding any power. The applications were not limited to the military scope. The knowledge about aerodynamics and propulsion fed the civil aviation industry and the first space projects. In less than a decade, the principles developed in Peenemünde allowed launching the satellites and ships that would initiate the space era. The closing of the German program did not suppose the end of the rocket. Its design was reproduced, improved, and multiplied. The name disappeared, but its structure continued alive in the missiles that marked the world politics during half-century. What began as a desperate attempt of Germany to maintain the war was transformed into the starting point of the modern technology of propulsion. The V-2 was more than a weapon. It represented the first time that the science reached the power of deciding the distance between the Earth and the space. Each launch, each trial, each explosion in Peenemünde or in the tunnels of the Harz was a step toward a new type of power, one that did not depend on armies, but on the domain of the knowledge. That project, born among ruins and darkness, changed the form in which the world understood the war, the technology, and the future. From the Reich to NATO and the USSR, the recycling of Nazi weapons. When the weapons of the Reich remained under Allied control, a stage of intensive use of the German technology by the winning countries began. Instead of destroying everything confiscated, many programs were oriented to taking advantage of the knowledge and the captured materials. The rockets, the engines, the automatic weapons, and the precision engineering were seen as valuable resources. What had been born to sustain the war of the Third Reich was transformed into the base of the post-war arsenals. In the United States, the move of engineers, pilots, and researchers marked the beginning of a systematic policy of talent absorption. Hundreds of specialists were sent to military bases where they were allowed to continue their projects under new orders. The works of propulsion and flight control were integrated into laboratories of the Army and into contractor companies. There, rockets, missiles, and guided bombs were rebuilt that no longer bore German insignias, but conserved their original structure. The tests demonstrated that many of those designs surpassed what existed in the American arsenal. The most emblematic case was that of the ballistic missiles. The engineers who had worked in the production of rockets were moved together with plans, pieces, and technical documentation. In test fields of the desert, experimental launches were realized with rebuilt rockets. Each test provided information about aerodynamics, stability, and control that the Americans used to develop their own models. From those experiences, the first middle-range missiles and the foundations of the space technology would arise. The knowledge obtained was so valuable that it was classified with the maximum level of security. The Soviets followed a parallel path. In the Eastern Zone, the teams of German engineers were moved with their families to special facilities. In factories reorganized under Soviet control, the production of engines and structures of rockets was resumed. The German technicians worked together with local specialists in conditions of isolation. In few years, that collaboration allowed the Eastern Bloc to have missiles based on the models of the Reich. From those adaptations, the rockets that later pushed the satellites and intercontinental missiles would be born. The United Kingdom also took advantage of the results of the German effort. British laboratories dismantled captured weapons and studied their mechanisms. The MP-40 submachine gun was analysed in detail, and several of its mechanical solutions influenced the development of British post-war models. Aviation engineers examined turbines and guidance systems, while military units evaluated German machine guns and rifles. In test fields and firing ranges, performances, fire rates and tolerances were compared. Part of those conclusions was incorporated discreetly into the modernisation programs of the British Army. France, which should rebuild its army almost from zero, found in the German material an immediate base to rearm itself. Thousands of captured rifles, submachine guns and machine guns were redistributed among its armed forces. In the national workshops, pieces of German origin were adapted to French calibers, and components of different origins were combined. Some factories incorporated confiscated machinery and patents to resume the production. With time, those same designs gave place to local models inspired in the Germanic engineering. Several weapons manufactured in the 50s conserved mechanisms almost identical to the originals. The tests with German armament were not limited to light weapons. In research centres of several countries it was experimented with artillery, automatic cannons and optical systems. The captured pieces were submitted to trials of wear and precision. In many cases, the conclusions served to establish industrial standards. The performance of the German machine guns, their reliability and their ease of maintenance became reference models. Some were copied almost without modifications and continued in service during decades. The exploitation of the technology did not stop in the mechanics. The production methods, the modular design and the German industrial organization were studied as an example of efficiency. The Allied engineers gathered thousands of plans and manuals that described processes of manufacturing in series. That documentation allowed modernizing factories and optimizing the production of armament. In many cases, the same German technicians supervised the adaptation of their methods to the new assembly lines in the abroad. The transfer of knowledge also reached the aviation. In the laboratories where jet engines were analyzed, it was discovered that the German experiments with mixed fuels and compact turbines were years ahead of their Allied equivalents. The tests with those engines gave origin to national programs of propulsion. Some captured German prototypes served as direct base for the first jet fighters produced in the abroad. The border between confiscation and cooperation became blurred, but the result was the total integration of the German technical legacy into the world engineering. With the pass of time, the adaptations derived from the captured German material had a direct impact on the post-war military technological development. What initially was a systematic seizure of weapons and equipment was transformed into a practical transfer of concrete technical solutions. Engines, guidance systems, automatic weapons and optical devices designed in the Reich were integrated into national programs under new denominations and industrial structures. The United States, the Soviet Union, the United Kingdom and France incorporated these developments according to their own strategic needs. The result was the silent incorporation of enemy technology into the emerging arsenals, not as political continuity, but as technical base for a new stage of military competition. Buried, sunk and forgotten, the hidden arsenals. The end of the war did not leave a country simply defeated, but a territory sown with dangerous remains. In the months of 1945, while the cities burned under the Allied fire, the German leaders applied orders that intended to erase the tracks of the war effort. Thousands of factories were disabled, entire depots of munitions were blown up, and many weapons ended buried under the debris or sunk in lakes and seas. Germany remained turned into a warehouse of ruins and scattered war material. The final instructions of destruction were transmitted in the middle of the chaos. As the Allied troops crossed the Rhine, the regional commands received contradictory orders. Some had to conserve the basic services, others should raise everything that could be useful to the enemy. In the industrial basins, the local chiefs ordered flooding tunnels, blocking accesses and hiding machinery in abandoned mines. In the Ruhr, bridges and steel plants were sabotaged partially to prevent their use, but the real damages mixed with desperate improvisations. The disintegration of the state turned each weapon depot into an autonomous problem, without coordination, without inventories, without central control. Meanwhile, the Allied aviation unloaded over the country a volume of fire never before seen. Between June of 1944 and March of 1945, more than 1 million tons of bombs fell over German territory. Berlin, Hamburg and Dresden remained turned into mountains of twisted iron. The arsenals remained destroyed, but many underground shelters resisted. In tunnels, mines and caves, thousands of tons of munitions and explosives were stored that could not be withdrawn in time. The defeat left buried a latent danger that would continue claiming victims during decades. The occupation forces found a confusing panorama. In fields and forests, cannons, disabled tanks and wagons full of projectiles appeared. In the ports of the Baltic, the German Navy had sunk in a deliberate way ships loaded with torpedoes, mines and drums of toxic substances. In the Baltic Sea and the North Sea, more than 300,000 tons of munitions were thrown to avoid their capture. During years, the fishermen of the zone continued finding projectiles, grenades and containers corroded by the salt water. The problem became a silent ecological threat. The reports of the Allied authorities mentioned hundreds of hidden depots. In salt mines of the center and south of Germany, metallic containers with poisonous gases were discovered, among them tabun and sarin. In some cases, the soldiers who entered to inspect the tunnels did not know what type of material they were stepping on. The mines of Die Herrenfurth and Gendorf were partially sealed and watched by Soviet and American troops. It was estimated that only in those facilities more than 12,000 tons of nerve agents had been produced, part of which never could be traced completely. Many of those arsenals remained without being recorded during years. In 1947, still thousands of tons of bombs without detonating in destroyed cities were recovered. The cleaning teams worked among unstable ruins and collapsed depots. It was calculated that for each demolished building at least 5 projectiles without exploding appeared. In Berlin, Hamburg and Essen specialized units in deactivation were established, but the rhythm of work did not reach to cover even a fraction of what had remained buried. The urban reconstruction coexisted with accidental explosions that reminded that the war had not finished completely. To this, the deliberate sinkings in lakes and rivers were added. In Lake Toplitz in Austria, metallic chests with documents, short weapons and false ingots used in the currency forgery operation were thrown. In other Bavarian reservoirs, boxes of munitions sealed with tar were found. Some of these depots were discovered by hikers and treasure hunters in the following decades. Many others continue under the water, inaccessible by the depth or the chemical risk that they represent. The chemical material was the most problematic. Large barrels with residues of mustard gas and tabun were buried or covered with cement in rural zones. During the occupation, the Allied technicians tried to locate and destroy those containers, but great part of the records had been lost. In some cases, the inhabitants of the neighboring towns were completely ignorant of what was under their lands. Decades later, agricultural excavations and public works would continue finding oxidized barrels that exhaled poisonous gases when breaking. The port zones also became cemeteries of weapons. In Kiel and Lübeck, the Allies sunk vessels loaded with artillery projectiles and aerial bombs. In some cases, it was a rapid method to eliminate the most dangerous material. The result was the creation of true underwater munition fields. With the pass of time, the sediments covered the loads, but the corrosion began to release slowly heavy metals and toxic substances. Posterior studies would calculate that a significant part of those munitions still conserved its explosive capacity. The storage of unusable material became an administrative problem. The Allied military authorities classified and destroyed more than 3 million light weapons, but thousands of pieces remained stored in hangars or basements. Some depots were closed without inventory. In the rural zones, the civilians found rifles and grenades that had been hidden by soldiers in retreat. Many of those finds ended in private hands, feeding a black market that persisted during the first years of the post-war. The attempt to erase the tracks of the war effort was incomplete. Under the new German cities, the foundations were raised over layers of steel and buried explosives. Each year, specialized teams continue withdrawing bombs without detonating. The modern reports estimate that more than 100,000 artifacts remain still underground. In the Baltic coasts, the remains of chemical weapons sunk during 1945 continue filtering dangerous substances to the sea. The hidden arsenals of the Reich, conceived as a form of denying the booty to the enemy, were transformed into a toxic and persistent legacy that no peace treaty could deactivate. The heritage that changed the war forever. Upon finishing the war, the world believed to have destroyed completely the war machinery of the Reich. However, a good part of its legacy continued present, camouflaged in research programs, reactivated factories and technologies adopted by other countries. The Nazi weapons did not disappear. They changed form, flag and purpose. What had been conceived for a total war became the base of the military modernity. The German lines of research did not stop with the surrender. The Allies moved thousands of technical documents and plans to their own laboratories. In them, formulas of fuels, detonation mechanisms and control systems were found that decades later would appear in missiles, planes and submarines of new generation. The long-range rockets gave origin to space programs, the jet engines, to the supersonic aviation, the studies of nerve gases, to international protocols about chemical weapons. Everything that had been designed for the war continued influencing in times of peace. The German engineers scattered by the world were key pieces of that continuity. Some worked for the winning powers, others emigrated to countries that sought to modernize their industry. In the United States and the Soviet Union, they participated in the development of ballistic missiles and satellites. In South America, their technical knowledge served to create armament factories and training planes. Even in neutral countries, the precision methods and the patents of special metals were incorporated without reference to their origin. The result was a silent network that kept alive the technological heritage of the Reich much after 1945. In Europe, the weapons that were not destroyed continued circulating during decades. German rifles, machine guns and pistols reappeared in colonial wars, civil conflicts and insurgent movements. Some models remained operative in regular armies until the 70s. The machine guns derived from the MG42 and the rifles inspired in the Mauser 98 continued being manufactured with new names but the same mechanism. The influence of that engineering extended to all the powers, from the British factories to the Soviet ones. The chemical and biological armament also left its track. The compounds developed in the German laboratories were studied by the Allied powers in secret. Part of those agents was stored during years in controlled facilities, while the scientists who had created them passed to work under new flags. The programs of chemical defense of the post-war were born directly from those investigations. What had been a prohibited arsenal became the base of new doctrines about security and deterrence. The war also had pushed the creation of industrial networks capable of producing in mass under any condition. That capacity was absorbed by private companies in the years of Reconstruction. The plants that before manufactured weapons passed to produce heavy machinery, engines and tools, but they maintained the same level of precision. In that way, the efficiency of the German war industry was transformed into the model of the modern European production. The machines that had served to manufacture cannons and rifles passed to build automobiles, planes and civil technology. The technical knowledge captured became a form of power. The seized documents and the confiscated patents were utilized without compensation, giving origin to innovations that afterward were considered national. In the Allied archives, more than 500,000 German patents transferred to foreign laboratories remained recorded. From those ideas, electronic components, materials resistant to heat, optical systems and techniques of welding arose that became essential in the industry of the 20th century. What once was a war effort ended up integrating itself into the technological base of the modern world. The consequences of that heritage were profound. The space race, the commercial aviation, the systems of guidance by radar and the intercontinental missiles were built over the experiments initiated in the final years of the Reich. The same ideas that had fed the destruction were utilized afterward to dominate the sky and explore the space. In each technical advance, there was an invisible line that returned to the laboratories of Peenemünde, to the tunnels of the Harz, or to the underground factories of the Ruhr. Meanwhile, the physical residues of that epoch continued emerging. In the northern seas and in the forests of Europe, the remains of the hidden armament continued appearing with the pass of the years. Buried munitions, sealed toxic gases and sunk projectiles reminded that the war had not finished completely. Each find reinforced the sensation that the heritage of the Reich could not be eliminated completely. It continued present in the air, in the earth and in the technology. The invisible legacy of the Nazi armament is not measured only in conserved pieces or copied inventions, but in the reach of its consequences in the long term. The powers understood that the military domain no longer could be sustained solely on the brute force, but on the capacity to absorb and develop technical knowledge. That lesson, arisen from the German laboratories and appropriated by its enemies, influenced in a decisive way the evolution of the modern war. The weapons of the Reich did not survive as objects, but as an operative principle. the conviction that the knowledge, even when it is born from the disaster, can be transformed into power. The winning powers understood that the military power no longer depended uniquely on the number of soldiers or on the extension of a territory, but on the capacity to sustain a permanent system of research, production, and innovation. That lesson, learned starting from the German collapse, became one of the pillars of the new international order. The science applied to the war ceased to be an exception to transform into a structural condition. At the same time, the heritage of the conflict remained integrated into the physical and human landscape of Europe. The reconstruction advanced over invisible remains, over decisions taken in the last months of the Reich, and over an industry that had reached its historical limit. The past did not disappear all at once. It remained absorbed in the present, silent but persistent. The weapons of the Third Reich did not survive as instruments of combat, but as a warning. They demonstrated until what point a modern state could mobilize knowledge, resources, and people to sustain a total war, and also they revealed the irreversible cost of that effort. The world that arose after 1945 inherited that experience and transformed it into doctrine, into strategy, and into system. Thus, the history of the Nazi armament does not conclude in the moment of the surrender, but in the form in which it redefined the relation between science, industry, and power. Not as a continuity of the Reich, but as a lesson that would mark the course of the following century.